We're going to do some guided exam question practice on the 2012 question that came up on the Rutherford gold foil experiment. It was worth 25 marks, so a half a question, 10 minutes on the timer. Let's jump into it. In 1909, Rutherford bombarded a very thin sheet of gold foil with these things called alpha particles, most of which passed straight through. So key word here being most of them. Most of them passed straight through, undeflected. Okay, so the parts just went straight, passed straight through undeflected. Some alpha particles, however, were deflected at large angles, and a very small number were reflected back along their original paths. Again, this is exactly what you would have learned in the experiment, so it's not like there's anything new here. The first of these observations was not inconsistent with the Plum pudding model of the atom, which had been proposed by Thomson in 1904. So it was not inconsistent, it matched the model, the Plum pudding model. Again, we're probably going to be asked about this later on. Most of the alpha particles could go straight through that, but Rutherford had to formulate a new model of the atomic structure to account for two other observations. So the other two observations, that some were reflected, some were deflected, and some came straight back. These were not expected from the Plum pudding model. All right, let's jump into the questions. Because again, the blurb can confuse us, but remember, it's all about the questions. There are some important information in the blurbs, but okay, first thing, part one, what? Describing what they are. Alpha particles. What are alpha particles? For 4 marks. Okay. Now, what are they is essentially what are they made of? That's what they want to know. They don't want to know that they're particles that were fired. They don't want to know that they were even positively charged. Is probably not enough here. We need to know explicitly what they are. So let's talk about, this is part one. What is an alpha particle? Now, again, my advice here to you is, can you draw and label an alpha particle? Do that now, pause the video and do that now. Okay, so again, my class, I would have drawn and labeled one for them. So this is what I would do. I've got 4 particles in an alpha particle. So there are 2 red ones and there are 2 green ones. Okay, so the 4 particles, 2 of one, 2 of another. Can you, if you weren't able to draw this already, can you now label this for me? Label what these 2 particles are. Okay, so you're playing if you've got this label diagram. Well, the red ones or the green ones, it doesn't matter which. It's important to note that 2 of them are protons. 2 of them are protons and 2 of them are neutrons. There are no electrons in an alpha particle, and this is why you may have learned that it's positively charged, because there's 2 protons which are positive, there's no electrons to balance that out. And essentially what this is the same as is a nucleus of a helium atom. 2 protons and 2 neutrons. So that's what people may describe it as. So when you draw it, it's always a good idea then to explain underneath what it is. It's a particle made of 2 protons and 2 neutrons. And 2 neutrons. Or some people, you may have learned it like this. It's a He, helium nucleus. All of this is scoring marks. You will probably score the marks for that, but it definitely don't just draw the diagram. As a backup is the diagram. It's a particle made of 2 protons and 2 neutrons. Definitely reckon we got the 4 marks there. Right, next one. Jump back over here quickly, because we're on the clock. 10 minutes. Describe the structure of Thomson's Plum pudding model. For 6 marks, again, highly recommend that you draw it first. So Plum pudding, draw and label it. Again, diagram's no good without labels. Pause the video, draw and label it. Okay, now that you've drawn and labeled it, I imagine most of you were able to do that. Most of you know what the Plum pudding model looks like, I hope. Explain it in words now. Pause the video, do that now. This is what I would have here. A circle with a plus in the middle. Remember, no nucleus yet. Plum pudding model didn't know anything about the nucleus. Okay, so it's a positive sphere. Positive sphere. Remember, this is a 3D structure, even though we can only draw it as 2D. So it's a positive sphere. That's 1 of the 3 marks, I reckon. And then there's something here. We've got these electrons studded in, or electrons embedded. Sometimes you'll see it written like that. But I'm happy with electrons are studded in. Electrons are studded in. That's the other 3 marks. Pretty straightforward, pretty simple, I reckon. We did perfect there. All right, let's go back to the question. Explain why some alpha particles were deflected at large angles as they passed through the gold foil. Okay, again, some deflected. Why were some deflected? Again, pause the video and try and draw me a label diagram of the alpha particles being deflected and why. Pause the video and try and do that now. Okay, all right, so this is what you should have done. You should only be playing if you've got this done. All right, so here is a couple of gold atoms. Okay, and we've got the positively charged nucleus in the middle. Okay, now, sorry, my OneNote is, oh, it might be okay. Here's the positively charged nucleus. And here's the positively charged nucleus and so on. So each of these gold atoms has a positively charged nucleus that Rutherford didn't really know about when he started his experiment. Okay, each of them is the nucleus. And then, so I'm actually going to label this the positive nucleus. And then here are little alpha particles. Again, they are also positive. So again, I'm going to try and draw. I'm not going to draw them as detailed as I did up here. I'm not going to draw them like that. I'm just going to draw them as little positive particles. All right, so the alpha particles coming in, and most of the time, its path is it will go straight through. Most of the time, goes straight through. So straight through. But sometimes, because it is positively charged, if it goes close enough to the nucleus, then it will get repelled because the nucleus is also positive. So this here shows repelled. The nucleus is repelled and because they are both positive, repelled. So this is a positive alpha particle. And the nucleus is also positive. We should definitely be using the word repelled. And a lot of my students' answers, they said the alpha particles are reflected because they go close to the nucleus. It's asking in the question, why are the alpha particles reflected? It doesn't want you to use the word reflected in your answer. It wants to explain what is reflection, what's causing it. And it's caused by the repelling of the positive charge of the alpha particle, positive charge of the nucleus. Now, if you didn't already, try and explain this now in words. I would like you to do that now, please. Pause the video, do that now. Okay, so what have you written? What you should have written here is that, where are we at? Yeah, so some alpha particles are repelled. Definitely is a key word you want in your answer here when you're talking about why they're reflected. Repelled by the positive nucleus. That's really it. That's as simple as it is. But again, if you don't use the word repelled in there, you don't use the phrase positive nucleus or that they has the same charge, the same positive charge as the nucleus, then you're just not hitting the key points. Okay. All right. Next bit. That was for 6 marks. Next bit. Why were some alpha particles reflected back along their original path? Reflected back along the original paths. And why did this only happen to a very small number of particles? Next one. So this is part IV. Reflected. Why were some reflected? What does that mean? Okay, so what I want to do, pause the video and show me some alpha particles being reflected now. Diagram. Show me a label diagram. Show me reflection. Okay. This is what you should have had. It should only be drawn if you should only be playing the video if you have this drawn. Okay. Here is again the gold atoms with the positive nucleus in the center. Okay. So the nucleus is here is an alpha particle, and it's coming in, and it's hitting the nucleus. So this time it's actually colliding with the nucleus. And it's coming back towards where it came from. Okay, this is what we call a reflection. It's different from a deflection. This is a reflection, comes straight back. So why are some of the alpha particles reflected? Again, it's because they actually collide with the nucleus. Okay, so few particles, or very small number, few particles reflected, Y dot 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 dot. Finish off the sentence. Pause the video. Do that now. Okay, so a few particles were reflected because they collided with the nucleus. Because they collided with the nucleus. Okay, now, why only some? Why a very small number? Well, the nucleus is very, very tiny, which means that the likelihood of an alpha particle actually colliding with the nucleus is very, very small. So why is it only a very small number? Because the nucleus was very, very small. Is very small. That's it. That's that simple. Okay, the next bit. Draw a label diagram to show the new structure of the atom proposed by Rutherford. Because remember what I said here? Rutherford had to formulate a new model of the atom, so the Plum pudding wasn't good enough anymore to account for two other observations. So he's discovered the nucleus. There was no nucleus in the Plum pudding model, and there was now that Rutherford has discovered it. So we definitely want to draw an atom that's got a nucleus and electrons somewhere outside the nucleus. Okay, so new model. Pause the video and draw what Rutherford would have done. What he would have drawn as his model. Pause the video, do that now. Okay, what you should have had is a nucleus. Very straightforward. That's what Rutherford's now discovered, the nucleus. And an electron or the electrons are orbiting somewhere around here. Doesn't know where, don't really know much detail about orbitals or even shells that came later with Bohr. But he knows the electrons are outside the nucleus somewhere. So long as you've drawn a label of the nucleus and you've shown the electrons are outside the nucleus somewhere in a shell or a cloud or something like that, that is the rest of the marks. Right, guys, pretty straightforward. I'm going to put up the marking scheme here for you to have a look through and see the different areas the marks we're going for. But like I said, the real area that might have caught you out was this stuff here and the detail around this. Part 3 and part 4. So really study there on what I've done and make sure that you are you're picking up all them marks. All right, guys, that's it. See you in the next video.